Okay, guys. Okay. So, what do you see here? No, that's not a Windows typical behavior. This is the universe at very early times. Okay? So now we start with fluctuations in the energy density that are extremely small and generated by inflation, as we discussed. What happens? We have a gravity, which is acting on our particles, on our fluids, and through the equation of motions that we studied, we are going to have an evolution. Okay? So wherever there are overdense regions, when some conditions are met, we can have the growth of structure. Okay? The growth of structure that we can study through the perturbative approach that we treated in the last lecture. Okay? We introduced a very small perturbation to the background, and we studied the dynamic of the perturbation fields. Nice. Let's try to see where we arrive with that prescription. So we are here. Okay? So you see, that's a time series, so that's a numerical simulation. The particles with brute force are let interact one with each other with respect to Newtonian gravity, of course embodying also an expansion of the universe just by stretching the coordinates. But this is what's going to have tiny fluctuations with respect to the background. If you think at the cosmic microwave background, actually these fluctuations are way too large. Okay? You will not be able to notice them because they are on the order of 10 to the minus 5 with respect to the background. Okay? So the density contrast, the temperature fluctuation contrast on the CMB are 10 to the minus 5. Perfectly in the linear regime. What you did, you can use it to describe the cosmic microwave background. Let's our time evolve. As the field is growing, you see there are kind of perturbations that are getting larger and larger whenever the collapse is possible, and therefore the fluctuations are getting larger and larger. Slowly, on certain scales, we are going out of the linear regime. Okay? We are going in the nonlinear regime. And we start to see the formation of filamentary structures. You can see they start to form, and the formation of galaxies. You see? They're starting to take place. Whoops, no! How do you go back? Okay. And you have the formation of galaxies. Okay, let's go from here. Highly nonlinear objects. Okay? So you have two things that are taking place here. Again, gravity, expansion. You might want to introduce also the interaction between the fields, as we said. We start from something similar. The time is evolving, and under certain conditions, we can have overdensities that grows in time. Okay? In the linear regime, now we make a slice. So this would be like the density fluctuation field in one dimension. For example, this is a slice along the x direction. We have one mode, which is characterized by a k, and then we might have the superposition of another mode with a larger k, so k mode 1, mode 2, where k2 is larger than k1. In this case, I draw it as larger in terms of the amplitude, but it could be also smaller. Okay, this is just to give you a sketch. And the density field that we would observe is the sum of these two. So we have this high mode fluctuation superposed to this one. So it's going to be something like that. If we only have these two contributions, of course there are much more contributions. Okay? And the two in the linear regime evolves independently. There is no power transfer from one mode to another. Therefore, the two amplitudes are really just going to scale. The power spectrum of these fluctuations is not changing. The shape is not changing. It's growing, but it's not changing. Gravity continues to pull. Matter is flowing this direction. These two guys get larger. This region gets depleted. Up to the point in which we don't have anymore this sort of fluctuations, but we are in the linear regime. Let's take this as a background. We have a total fluctuation field, which is going to be given by something like that. For example, if we have these two structure collapses, that's what we are going to have. You see, that's very different from the superposition of waves. We are in the nonlinear regime. Non-linear. How do you describe it? We were working here. How do you describe something like this? You need an embodied numerical simulation, such as the one that I showed you. Okay? You need to use brute force and solve the Euler, the Poisson, and the continuity equation in their full power, without linearizing them and just tracking very small perturbations. There you have the full picture. Or you can use the Zeldovic approximation to go to higher orders, not to have a full picture like this one where you have the formation of galaxies and the dynamic of galaxies and all of that, but you have a description of much higher frequencies that we did in the cosmology lectures, okay, the past semester. Now what I'm going to do is something different that we haven't done in those lectures, which is to go from first order perturbation to second order. Okay? Where we will be able not to describe our density contrast field like in a numerical simulations, but we will be able to do it in a mildly nonlinear regime, where there has been some power transfer between K modes. Okay? This we will be able to do it. And we will be able to do it not with numerical simulations, so for brute force with the computer, and just see where particles are moving around, but with equations that we can write in principle at the blackboard. I'm not going to use the blackboard because, you know, from what we had before, the equations are going to be larger. The concepts are going to be simple, but the equations takes time. Okay, so I'm going to use the beam for practical reasons, and to try to keep the focus on the meaning of the equations instead of just tracking large equations around. One other thing that I would like to tell you here is that the linear regime, so it's not only a time scales that set whenever we are in a certain, if we are in the linear regime still or in a nonlinear regime. Okay, it's also a matter of the wavelengths, because smaller wavelengths, so modes with higher frequencies, enter in the nonlinear regime earlier with respect to larger scales. Okay, therefore, even if we observe the galaxies at very low redshift, on small scales we are in the nonlinear regime because the fluctuations are large, but on large scales the fluctuations are still in the linear regime. Okay, that's why, for example, the clustering of galaxies, the study of the clustering of galaxies, can be performed in the linear regime, or better in the second order, so with the mildly nonlinear regime that we are considering, because the perturbations are there, but on large scales they are still nearly linear. Okay, so time, it's a matter of time and wavelength, if we are in the linear or nonlinear regime. That's a key point. Good. Let's dig into the equations. So, let's get the simulation out of the way, and here we are. So, this chart, and we are here. Then, of course, when you want to look at the equations, you have the notes, so you can look at the mathematics which goes in between. Okay. Anyway, here we are. So that's what I just said. Namely, we are going to consider moving to a non-linear regime, and there's some in a nearly non-linear regime in which even at low redshift do not occur on T scales. So when you're talking about 10, 15 megaparsecs in terms of wavelength at low redshift, we are still in the linear regime, but at smaller frequencies, or smaller K modes, we are in the mildly nonlinear regime, okay, if we are talking about these scales. On even smaller, it's highly nonlinear, and you need numerical simulations, there is no way out, okay? Good. These are the assumptions that I'm going to use. So we are going to consider only scalar perturbations. That's what we did so far, where the velocities are going to be irrotational. Again, that's what we did so far. We are going to consider perturbations within the horizon, okay, such that we can neglect some of the relativistic terms. Non-relativistic particles, such that we can neglect all non-relativistic terms. All relativistic terms, and we are going to consider dust, okay, dark matter. So that's the assumptions that we're going to use. Under these assumptions, what is the set of the equations that we're going to deal with? Well, the continuity equation, the Euler equation, and the Poisson equation. So we have a set of equations, the hydrodynamical equation within a context of gravity. Okay, so we have a gravitational force acting onto a fluid characterized by those particles. And these are the equations that we did so far, but with the approximation aforementioned. So therefore, we are in the Newtonian gravity, that you can clearly see, and no relativistic fluids within the horizons. Okay? But the equations are always the same. And here we didn't introduce any linearization. They are full, okay? They contain all nonlinear terms. They are all there, okay? Then what we do is just a little bit of massaging of this equation. For example, we do derivatives. You see the prime is not anymore with respect to the conformal time, but is with respect to n, which is the logarithm of a. That's just how it is defined. We move to co-moving coordinates, such that we are tracking the proper motion of particles, not the one due to the cosmic expansion. And you see it here. So the velocities of particles are due to the cosmic expansion that enters through the expansion rate, and then you have the proper velocities. Okay? And yeah, that's it. So this is basically what we also did already in the non-relativistic treatment of perturbation theory that we did in the cosmology lectures last semester. Okay, so that's in the and once you do all of this, reshuffling of the equations, this set of equations become this one. Okay, here nothing happened, just a little bit of massage. We are still in the full. We are still capturing the entire physics, okay? Then what we do, we combine them. And we opt, so we basically, you see, we have the potential, we compute the divergence of this equation, such that we have a nabla square here, and we can get this one and plug it into here. As well, we can merge this one with this one, because through the velocity field, okay? We can then put all the three equations together. That's something that we already did, so I'm not going to the details. And we arrive to our beloved equation characterizing the matter fluctuations. We have already seen this several times. The only difference is that it is in a Newtonian limit within the horizon. That's for dust, okay? And we are in full power, okay? You see, we have the equation that we studied before, where we have, before what we did, we linearized these expressions, and we obtained this equation equal to 0. Okay? These were the expression, the one that we derived earlier, that were valid in the linear regime. All the non-linear terms that are contained in this expression are these ones. Okay, so that's the perturbation equation for the density field that characterizes all scales at all fluctuation modes, including the nonlinear regime. Okay? So again, same physics. The only difference is that we kept all orders at higher order terms. Okay? Nice. Now that we have this expression, we need to solve it. We need to find a solution, which is difficult unless you expand your density field into a perturbation series. Okay? So, what do we do? Well, first of all, before arriving here, we simplify a little bit our life because we get a simpler cosmology. So I'm going to treat the case for an Einstein de Sitter universe. I recall you, the Einstein de Sitter universe is the one dominated by matter and where the curvature is equal to 0. Okay, so it's a fully matter-dominated universe. In this case, then h prime over h is just minus 1/2. The expansion rate is just equal to 1 by definition because of omega. Remember that we had before this approximation describing the evolution of the perturbation field, but omega is equal to 1, and therefore also the expansion rate is equal to 1. Okay? Therefore, we have these simplifications, tick, 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 that we can plug in into our perturbation terms. And we get simplifications. Therefore, these guys are the nonlinear terms. Okay? These are just the nonlinear terms. You see that we have, we want to keep order, not the first order, but second order terms. Okay? So we keep up to that one. The fourth order terms, we neglect them. Okay, that's because we are going the direction of this expansion. Okay, only up to second order. Therefore, what we do? Here we have this product. We have delta, and then we have a delta prime to the power of 2. That's third order. We neglect it. Okay, therefore this guy goes away. There is 1/1 that remains. F is equal to what? That's equal to this guy, f prime over delta, which is our f. That's equal to 1. Okay. And then just continue, it is just what I said simplified, omega m is equal to 1, that's equal to 1. Therefore, all of these terms are just that. At second order, not first, second order. Then what we do? Okay, so we are performing this expansion into first order, which is the one that we studied so far, and the one at the second order, which is the one that we want to investigate. Therefore, what do? We get our delta, and we plug it into here, 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 and here. What are we going to get? This long expression, okay? Long expression, where I just show you here, you see, just for simplicity, you see, this is delta double derivative, this is our delta double derivative, where we also introduce the growth factor. Okay, so we are going to have a growth factor for the linear term and a growth factor for the nonlinear term. Okay, and the same is for the other equations. But then what we know? We already solved the linear part of these equations. Therefore, we know that this guy double derivative, this guy first derivative, plus this guy first derivative is equal to 0, because that's the solution at first order. And therefore, whenever you find the terms with a G1 for the expansion rate at first order, that's going to be equal to 0. And therefore, this expression, the full expression here, is going to give you the solution for the perturbation at second order. Okay? Well, okay, then you neglect this one because it's at fourth order, so you just neglect this term. So you have this much simpler equation now, because you already know the solution at first order. You just solve it, it's a very simple step, and you get the evolution, and you find out that the evolution, so you use these ansatz, okay, but to solve this equation, and you find out the evolution of the growth factor at second order is proportional, so you have a proportional constant, to the power of 2 of the growth rate at first, the growth factor at first order. What does it mean? It means that whenever you solve your equations at first order, you also know what's happening at second order. Okay? But through this expression, you have the equation that is telling you that. So with this trick, we can move to second order. Okay? Good. What about other cosmologies? Well, you have to go numerical. You don't have an analytical expression for that. But in any, so because you see here we are using a very simplified version for Einstein de Sitter, so you could have also non-Einstein de Sitter universe, but then you get to have a numerical solution. Now notice to happen that nature, if you wish, or math was kind enough such that this expression is a very, very good approximation in general. Okay, what is going to change is basically the factor in front. Okay, so in general, that's the expression that you get. Second order is proportional to first order to the power of 2. Okay, that's what you get. Then we can continue, and yes, that's interesting. So we know what is the growth rate of our function. So you see that we are going to have our linear growth, the one that we already know, plus an additional growth. So when you enter in the nonlinear regime, the growth gets a little bit faster. Okay? But that's not the entire story, because we can, out of that, we cannot compute the power spectrum. Power spectrum that allow us to study the amplitude of the perturbation at different case, for example, by studying the distribution of galaxies or of galaxy clusters. Therefore, what we have to do is to get our expression and move into the Fourier space, such that we can investigate each k-mode independently. Okay? Good. So let's do that. Let's start with the continuity equation. Continuity equation that in full power is this one. Okay? Here is expressed in terms of density. Here is expressed, if you divide with respect to the background, that's computed with expressed in terms of the density contrast. Okay? So you perform the Fourier transform, which is just that in general, and you perform the Fourier transform of this side of the equation and the Fourier transform of this side of the equation. The Fourier transform of this side of the equation is just that. The Fourier transform is just, you see, we have the gradient, which is here, 1, which remains so. Then we have the Fourier transform of rho, and then we have the Fourier transform of the velocity. Okay? Then what we do, we just continue with our expression and we bring the gradient inside the Fourier transform. Because you know that in the Fourier space, derivatives are products of k modes times E. Therefore, if we bring our gradient to our integral such that we can express it as in Fourier space, that's what we get. We get the EK. Where we have a sum of k1 and k2 because we have the product of these two integrals. Okay? That's why you get this plus here. Once you have that, that's your expression. You can then make the back Fourier transform such that we can extract only the k expressions with respect to k mode. How does the back Fourier transform works? Well, you are just integrating your function with respect to the three-dimensional space. Then there is a normalization factor that depends on how you define the case with respect to x, but what you're basically doing is to integrate with respect to x to the power of 3, to the three-dimensional space, and then you have the inverse, the terms that express the inverse Fourier transform. Again, for this side of the, where is it? For this side of that's rho, should be delta, sorry. For this side of the equation, therefore you have this additional integral with respect to q and the Fourier mode of this guy, that gives you that. Why? Well, by construction. You have a function, and then you go in the Fourier space, you apply the inverse function, you go back to what you had before. Okay? And this is happening because the integral with respect to space of this exponential is actually a Dirac delta that selects only the modes which are equal one to each other. Okay? Therefore, it's going to select k1 equal to k3, and this shouldn't be here, sorry, because we already performed the integral with respect to space. So that's actually like that. Okay? And then through this delta function is just acting, and we get that the left-hand side after the back Fourier transform becomes that. Okay, again, I'm mistaken with rho, should be delta. Okay, so this is a delta. Then the right-hand side, so all of this stuff here, basically same concept. We apply the back Fourier transform. Our delta function is going to pop up, and we end up with this expression. Okay, that's once we are back to once we apply the back Fourier transform to isolate the K modes. Okay, and in the process, this is again full power, but what we are going to do is to keep only up to second order. Okay, and now look what happens. We have this expression, and we keep everything up to second order. We have this expression, and you see it's just multiplied by k, so we have to keep all terms up to second order. So second order, second order. But look here, we have the product between the density contrast of matter and the velocity, the proper velocities. And therefore, this must be first order and first order, such that the product of the two is at second order. Okay? That's key. That's key. Because this means that we can use the first order solutions that we derived earlier to quantify the entire term here. Okay? Good. Then what we do? We just, you see here we have our velocity field. That's a little bit annoying. That's why we go to a scalar field by using our computing the divergence of the potential. Out of this expression, we have a relationship between theta and k, which is just like that, just multiply times k and invert with respect to v, and that's what you get. So it's a very simple expression. And then we have that from linear theory, we have a relationship between the density contrast and the velocity gradient, the gradient of the velocity field. That's from linear theory, okay? In the appendix, boom, 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 here at the end, you see how this is about, okay? These are very simple steps, but keep in mind that in the linear regime, we have three expressions that are equivalent. And we can always link the density contrast to the velocity field, okay? In the linear regime. And here we do it. Where are we? Where are we? We are here. Okay, so and therefore our delta can be related to the velocity in the linear regime. Why is this linear regime relevant? Because here we need the linear regime. Okay, so we can get these two guys not with respect to delta but with respect to v, but twice with respect to the velocity. Okay, and we can do that because there we are at the linear regime. That's important. Okay, so we do that. We use our expressions that we derived here and here and here, and then we obtain just by dividing with respect to our h tilde, we arrived at this expression. Okay, so that's this expression. We divide by h after using this link to linear theory, and we arrive at this expression. So this is this guy here. Okay. What do you see here? You have the two velocity gradients normalized with respect to h because that's what we divided in this step here that are coming from here and here. Okay. Then we have the growth factor that is split. So you see there is a 0 here because there is the initial amplitude times the growth. Initial amplitude times the growth. And you have a prime here which is coming from the f. Okay? Here we have f, which is, no, I don't see it anymore. It should be here. I think I forgot it. So here is a divided f that gives you this prime. Okay? Just by using the definition of f itself. Okay? Just definition. So what do we have here? The key point is that you have a kernel, which is this guy. It's called kernel because it just contains k's, which are, if you want, part of this integral. Okay, so that's a kernel integral. Then you have the quantity that you want to characterize, which is the product of these two guys here that have been linked through linear theory such that you have two velocities. and then I split it into terms of growth factors, okay? So you have a kernel, you have the quantity that you want to characterize, and you have the growth factors that characterize their time evolution, okay? And then you have the delta function, which is coming from the previous expressions. What is a little bit annoying here? A little bit annoying here is that this kernel is not symmetric. Not symmetric despite the fact that K1 and K2 have the same meaning. These are just 1 and 2 just denote integral variables. And they have the physical meaning. Therefore, it's very convenient, or typically what is done is to symmetrize the kernel. Therefore, you get this expression, and you get just its value plus its value where you flip 1 with 2. Divided 2. Because this is equal to that, and you divide it by 2. Okay? And you get this expression, which is mathematically cuter because it's symmetric. Okay? With respect to K1 and K2. So by making this symmetrization, this expression gets this shape. And look that this expression is going to be always this sort of structure, integral, kernel, variable, delta. You find it all over the places. The Poisson equation, we can do all of this process also for the Poisson equation, will have exactly the same structure. You are going to have the linear regime. So in the previous expression we had this equal to 0. As for the continuity equation, where we have this one equal to 0, this will be our first order linear regime perturbation that we did before, on top of which we have our corrections that have exactly the same structure. Integral with a kernel, the quantity that we are integrating over, and a delta function. Okay? The procedure to arrive at this follows exactly the same steps. Okay? So these are our two equations, continuity equation that includes the perturbative term of second order. We have the Poisson equation that contains the perturbative orders up to second order. Okay? Then what you do, you solve the system of equations. Therefore, you get the time derivative of equation A, which is the continuity equation, and you plug it into, you see, you get a delta, a V prime that you plug into here. Okay? Time derivative, and you plug it into here. So you combine basically these two equations, and you get this expression. Okay? This expression where I defined all the perturbative terms here as C, and all the perturbative terms here are E, that you can find here. Okay? You see you have a C prime here because we made a time derivative of this guy. Okay? So this is just equation A, continuity, and Euler equation combined together. Okay? Then what we do? We have to plug in our deltas considering the perturbation not just at first order, but also at second order. So we plug it into here. We know that the first order terms are going to give you 0 contribution because we already have the solution at 0th order. So we are, like as we did before, we are going to have this expression for delta 1 that we know to be equal to 0. That's we find it before earlier. So what are going to survive are only the deltas, the perturbation at second order. Okay, so this expression we contain only perturbation in second order. Again, you have a differential equation that you can solve, and that's the solution of your differential equations. Once you plug back in C, E, F, and C, where F and K, F and S are defined here, you get this expression. That's your solution. Okay? Solution up to second order. Okay, it's not fully explicit because there is this integral to be solved and you do it numerical, but is your analytical expression giving you the solution of your perturbation at second order. Okay, so this one is your perturbation, where you find the first order perturbation, which we have the solution from the treatment that we did earlier, And here we have the second order contribution that you need to add to the first order contributions. Okay? That's your expression at second order. Okay? We can stop here. I've lost track of time, sorry. What we're going to do later on is to basically get our expression and compute the power spectrum, which is what we can quantify by observing the distribution of galaxies. Okay? Good. So we can stop here. Sorry if it took longer than expected, but I have only another lesson left, and I want to arrive at the conclusion of these topics. Okay, I see you later at 2:30. Okay? Thank you very much. I see you later.